Okay, so extraction of metals. Now, metals, most of them, the reactive ones, exist as compounds. They are trapped in ores or rocks under the ground, in their minerals. So to get them back to being a metal again, we have to take them from their oxidized state, give them some electrons, and we get the metal back. This is obviously a gain of electrons, so it's reduction. General equation, just imagine you've got a metal of 2 plus valence, or 2 plus charge, so a valency of 2. If we give it 2 electrons, it becomes the metal again. We've mentioned this before. The method of extraction will depend on the reactivity of the metal. So the most reactive metals are extracted by electrolysis. The more reactive the metal, the harder it is to extract. So obviously these metals didn't really exist in abundance until we had lots of electricity to be able to produce them. They're still quite expensive because making them using electricity is an expensive process. Underneath carbon in the reactivity series, they can be extracted by carbon or carbon monoxide. They're reduced by carbon and carbon monoxide. So carbon and carbon monoxide are reducing agents. And at the bottom, they're going to be extracted quite easily by chemical reactions, or they're found in their native form. Let's have a look at some examples. Copper. The mineral, a typical mineral that contains copper is called chalcopyrite, mainly copper 2 sulfide. And if we roast it in air, so we heat it to a high temperature in air, it gives us the metal, and the sulfur combines with the oxygen to give sulfur dioxide. So we get the metal copper quite easily just by roasting copper 2 sulfide, chalcopyrite in air. Zinc, it occurs as zinc blende, which that's the mineral, which is mainly zinc sulfide. And we can roast it in air in the first part of this process to produce zinc oxide. Now, zinc's a bit more reactive, remember, than copper. So it doesn't automatically give us the zinc metal, but if we heat it strongly in air, we get zinc oxide and sulfur dioxide. We'll need to balance that equation, won't we? So, why do we need a 2 here? Well, there's an odd number of oxygens here. Oxygens come in packets of 2, so we're going to have to make that number even. So let's try 2. 2 oxygens here. That means we need 2 zincs. So we've got to put a 2 in front of this. But now we've got 2 sulfurs, so we have to put a 2 in front of the sulfur dioxide. And then the oxygen, because it's on its own, is a bit more flexible. So now we've got 2 times 2 is 4, plus 2 is 6. 3 packets of 2. It's good practice. The oxide then, the zinc oxide, is reduced with carbon monoxide as the reducing agent. So we take away the oxygen and we get the zinc metal. It's probably in its liquid form when it's produced because it's quite a low melting point. Iron is produced in a similar way, and we'll talk about that below. Aluminium, think back to year 10. Alumina, which is aluminium oxide, we reduce it by using electricity. And this is because aluminium's more reactive, isn't it? So the overall reaction for the process is that, to get aluminium liquid. This was the diagram you saw last year. Okay, the cathode is the lining of this particular vessel. The aluminium forms at the cathode and the molten aluminium is taken out. The anode is dipped into the mixture, and at the anode you get oxygen gas produced. And as it says here, this means that the oxygen reacts with the graphite anodes to produce carbon dioxide. So the anodes must be replaced periodically. The mixture isn't liquid alumina, it's alumina dissolved in cryolite. And remember, we do that to reduce the melting temperature so that we don't have to use as much energy to melt this electrolyte. Okay, have a go at questions on the pages indicated.